All right, let's talk about something that'll stop you dead in your tracks, the dreaded 24 overload alarm on a Mazatrol control. If you've seen it, you know the frustration. Today, we're going to break down exactly how to beat it using a real-world case study. So, there you are. The machine's down, production has ground to a halt, and that alarm is just blinking at you. 24 overload. Where do you even start? It's a tough spot for sure, but here's the thing. There's a method to the madness. A logical path can get you right to the root of it. Okay, so let's jump right in. What were the very first signs of trouble? Because, those first alarms are your breadcrumbs, or so you think. In this case, they were actually a bit of a red herring. Right off the bat, the machine started throwing these 24 overload alarms, but with a bunch of different codes. You see the AN059, AN058, and AN05A. The key thing here, it was intermittent. It wasn't just one big, hard failure. That's always a dead giveaway that you're hunting for something a little sneakier, something hiding in the system. So the first logical step, right? You gotta check the hardware. Let's dive into phase one, the initial mechanical and system checks. This is where everyone starts. And look at this timeline. The first alarm pops up just after midnight. By that night, they're running tests. The next day, they're checking hydraulic pressure, trying to force the error to happen again. We're talking about almost 2 full days of just grinding it out, chasing down every possible mechanical lead. But, and this is a big but, they were barking up the wrong tree. And here's the usual list of suspects, right? This is troubleshooting 101. You check the motor insulation, you look at the balancing valve pressure, the modular valve, the whole counterbalance system, even the ball screw assembly. They did exactly what you're supposed to do. They went down the list one by one. And here's the frustrating part. After all that time, after replacing parts, after checking everything twice, the problem was still there. That alarm just kept coming back. This is that moment, the one where you have to step back and say, okay, it's not mechanical. We've been digging in the wrong spot. All right, so if it's not mechanical, what's next? You pivot. You have to. It's time to move on to phase 2 and start digging into the electrical circuit, the brains of the operation. Now this is the aha moment. The team says, okay, let's test the motor by itself with no load. And what happens? The motor works perfectly fine, but it throws a totally different alarm, a feedback alarm. And that right there was the game changer. It was the clue that cracked the whole case open. So what was actually going on? Well, the CNC was getting mixed signals. It was like it was listening to 2 people telling completely different stories. The motor's encoder was shouting, hey, I'm spinning over here. But the ball screw's encoder, since it wasn't connected, was just sitting there silently saying, nope, nothing's moving. The CNC didn't know who to believe, and that conflict is what was really causing the problem. And that leads us to the solution. Once they understood that feedback conflict, everything clicked into place. The problem wasn't a broken part, it was a logic error in the feedback loop itself. Okay, so check this out. The system was originally set up with what's called a full closed loop. That's the one on the left. The solution? It was to change it to a semi-closed loop, which you see on the right. This visual really says it all. The whole problem was hiding in the way these 2 systems work. So what exactly is a closed loop system? Think of it as a system with a built-in fact checker. It uses 2 sources of information, an encoder on the motor and another one on the ball screw. It's constantly comparing what the motor thinks it's doing with what the table is actually doing. It's all about maximum precision. A semi-closed loop, on the other hand, simplifies things. It says, you know what, we're just going to listen to one source of truth, the motor's encoder. It takes what the motor is doing and calculates where the table should be. By switching to this, they effectively told the CNC, just ignore that second conflicting signal from the ball screw. Problem solved. So how do you actually make this change? It's not about tools, it's about parameters. It's surprisingly simple, really. Just 4 steps. You change parameter SV017. Then you change SV05. Power the whole thing down and back on again. Test the access. And that's it. A few simple changes in the settings, and the problem that had them stumped for days was just gone. All right, let's wrap this all up into a handy checklist. Think of this as your game plan for the next time you're staring down a stubborn alarm. Here it is, your troubleshooting roadmap, broken down into 4 phases.
Phase 1, you always start with the mechanical stuff. Check the valves, the motor, all the physical bits. If that doesn't work, move to Phase 2, electrical. Try to isolate the motor, see if you can trigger a different alarm. That's your clue to move to Phase 3, system logic. Figure out if you're dealing with a closed or semi-closed loop. And finally, Phase 4 is the solution. If you need to, you go in and modify those parameters. Simple as that.
So what's the big lesson here? It's that sometimes the fix isn't about replacing a broken part, it's about reconfiguring the system's logic. It's a powerful reminder that you have to understand not just the what, but the why of how your machine works. The solution wasn't a piece of hardware, it was a shift in thinking. So, next time a complex alarm pops up, what are you going to do? You've got the process now. Start mechanical, move to electrical, and then dig into the system logic. Armed with this approach, you can take on just about any challenge that comes your way. So the only question left is, what are you going to solve next?